Okay, so we were just talking about the grad B drift, right? So we said, we showed here how we did it a little qualitatively and then somewhat more quantitatively later on. And the main thing to keep in mind is that, well, the grad B drift is perpendicular to both B and gradient of B, right? It depends upon the kinetic energy of the particle. It goes there's a B cubed in the bottom, although there are B's here, remember. Think about this. Will this lead to a net current though? And there's a reason. I mean, remember when we were talking about the E cross B drift or the G cross B drift, in all these cases, we keep bothering about whether this kind of a drift will lead to a net current. You see, there's a reason. I don't think in this class we will ever reach that level where we start talking about plasma instabilities and so on and so forth. But the thing is, a current channel, maybe we will, by the time we come to magnetohydrodynamics, maybe we will start talking about the kink instability and things like that. But the point is, if you have a net current, a current carrying plasma is subject to a whole host of instabilities. Okay, and it's important to know whether such currents can be spontaneously produced, and therefore is the plasma going to jiggle and wiggle as a result of this. Okay, this is why this is the practical reason we worry so much about whether there will be a net current. Right. Okay, another kind of drift which is slightly more easily understood is what's called the curvature drift. What if the magnetic field is curved? Okay. This can be explained a little more easily. And it's as follows. Well, the magnetic field is curved like this, and the particle is gyrating, and we can assume that the guiding center approximation is still pretty good, in that one can average over the fast motions and concentrate only on the guiding center like so. And now the guiding center, you can think of it as experiencing centrifugal force like this. It's called the curvature force, mv squared over r kind of force like this. Okay, where this v is the parallel v, the v parallel to the b. Okay, now if you have that kind of a force, you draw an analogy with the E cross B. It's as if this F is actually an E. Okay, so you to immediately write down the drift velocity, and you immediately get a curvature velocity which goes like this, and it's perpendicular both to the radius of curvature as well as the direction of B. Okay, so this is the interesting thing. The force is along the along the radius of curvature, but the drift velocity is like so. This is the direction of the radius of curvature, and this is the local direction of B, which keeps changing. If it did not keep changing, then there's no question of drift, of course, and the drift is perpendicular to both. That's what emerges from this. Once you write this down and you draw the analogy with the E cross B drift, the rest is very simple. Okay, nonetheless, I urge you to, again, I'm going over this fast. I'm simply illustrating, I'm picking the shortest way to illustrate the basic point without getting too encumbered in the details. And but I urge you to think about this carefully. I believe this is, I don't remember where this treatment is from. I believe it's from Starok. I think so. I've forgotten what I've taken. Either way, I've taken it, I've taken it in toto from one of these two sources. You can be sure of that. If you thumb through the books, you'll find it. Okay, so this is the other kind. So we've talked about a gradient of B drift. Well, we've talked about E cross. In terms of inhomogeneous magnetic fields, we've talked about the gradient of B drift, and now we're talking about the curvature drift. Okay, some points to ponder. How about gradients in density? There are such things as gradient of N drift. Okay, and can particle drifts always be identified with a bulk current? We've raised this point one or two times before. You've seen that, for instance, the G cross B drift can indeed be identified with a bulk current. The E cross B drift cannot be, because both the species are drifting in the same direction. And if I remember correctly, even if they were, I mean, if the forces were different, the velocities were different, then you could have a bit of a lag, and there could be a net current. But yeah, so please think about this point very carefully. Okay, now remember, in thinking about it, I would like you to keep in mind that a macroscopic current density is constructed using a bulk density and a bulk speed or velocity, not from, both bulk quantities which involve averaging over a particle distribution, not just from a single particle. All right, so please keep this firmly in mind. It's not quite the same as an individual particle, even if one is averaging over fast time scales for an individual particle to get the guiding center motion. That is still an individual. The guiding center motion is still for one particle. Whereas a bulk, current density comes from, an aggregate over all particles. Okay, so you can multiply by the particle density. That's okay. But if there's just be careful about this. All right. Okay. So now we talked about gradient of B drifts, right? But the gradient of B in the case that we talked about, you see, was like this. The gradient was, so the gradient, the B was pointing out of the page, and the gradient is perpendicular to that. How about now if you have a gradient of B along the direction of B? B is pointing in this direction, and the B field lines are converging or diverging in the same direction. This is what would be called a longitudinal gradient. B varies in the same direction as V parallel, and the gyro radius gets tighter because you've got a larger concentration of B field lines as you go farther. In other words, the B field is increasing in the Z direction. The gyro radius gets tighter. Remember how the gyro radius has the B in the denominator. So larger B means a smaller gyro radius. Okay, and this is a configuration that's of considerable practical importance, as we will see. I'll try to explain this. Okay, right. So, okay, I think this treatment is from Arnab Rai Chaudhury's book. This is the famous magnetic mirror. Okay, so here we have a situation where the B increases with Z until it flattens out. So please keep this flattening in mind as we go ahead and try to understand this. All right. Right. Okay. Now, this is always true. The divergence of B is always 0. And you write this down in cylindrical coordinates. Okay, this is simply divergence of B written down in cylindrical coordinates. Okay, and so the R would be this kind of coordinate, and the Z is like this, cylindrical R and Z. And just, so we neglect the radial variation. We take this to be a constant, okay? Constant along R, okay? There is no, so dB dZ is the same for any radial slice, so to speak. Now, this gives, you integrate, what you do is you take this to the right and you integrate, by virtue of this assumption, you can take this to be a constant. Okay, you pull this out of the integral. And the r prime is just a dummy variable. What you do is, like that. You take the r on the right and you integrate, and so the r prime from 0 to r, it just gives you 1/2 r square. And by virtue of this, you're allowed to pull out, this is not a function of r, so you pull it out and you get like so. Okay, now it turns out that, now this is in anticipation, turns out that there is a longitudinal, by longitudinal, a z-directed force on the particle. Okay, that's not yet clear. We will see how it comes about in a second. Right. Now, the f of z is q v phi br over c. Well, this is written in CGS units, which is why you have the appearance of this c, velocity of light. So this is simply f equals q v cross b over c. Okay, so the z-directed component of f would have the v phi times br. That's the only way you'll get a vz. All right. So, and the q is just the q is, you just take the modulus of q to get rid of this pesky negative sign, and this we call v perpendicular. The v phi we simply call v perpendicular. Well, it's perpendicular to z, so anything along z we call it parallel, and anything perpendicular we call perpendicular. And we retain this br. And you know what we're going to do next? We're going to substitute for this br from here, right? Okay. And also using r is equal to, okay, what's the value of r we want to use here? We want to use a particular value of r. We want to use the Larmor radius, right? And the Larmor radius is just the v perpendicular over omega, where omega is a Larmor frequency. Okay, so the Larmor omega is just a Larmor frequency, which would be how does this go? Like that, something like that, centimeter per second over centimeter, yeah, so something like that. Okay, that's the Larmor frequency. I suppose I should have mentioned this a little earlier on. I kept going, I just kept assuming that you would be thoroughly familiar with the Larmor radius and the Larmor frequency, gyration radius and gyration frequency, especially since I had assigned it in problems at 0. Okay, anyhow, so you plug this, you use this for r, right? And here in place of r, you use so the r's cancel out, or there's only one factor of r, and in place of r, you plug in a definite value for r, which is r sub l, yeah, and you use so this would be the kinetic energy, the quote unquote perpendicular kinetic energy. So it's in the same spirit as we said, although energy is a scalar, you can think of it as a kinetic energy associated with the perpendicular particle motion. Okay, then you get the z-directed force is like so. Okay, where this you can simply write as the gradient of B. Okay, and this you write as mu, the magnetic moment. Okay, so this is what's called the magnetic moment. And this is a very important result. You see, so that is, as the particle is spiraling this way, it feels, by virtue of the fact that there is a non-zero, there is a non-zero dBz dz, there is a force on the particle in this direction. And that depends upon how much, what's the longitudinal gradient of B. That's evident from this formula, you see. It depends upon the longitudinal gradient of B. Okay, and there's a minus sign here, which means that a positive, so a positive particle, it faces a mirroring kind. It's as if the particle is mirrored. Okay, in other words, the particle is reflected back. Okay, this is the particle tends to be reflected. The particle is traveling this way. Its gyro radius gets tighter and tighter and tighter, and at some point it gets mirrored back. The other thing to note, the mirroring is not immediately obvious. Why it should? What this formula tells you is that there will be an opposing force. That's what this formula tells you as such. The longitudinal force, although it depends upon the gradient of B. So if the B flattens out, then the force disappears. That's also what this formula is telling you. Okay, so right. So it hints at the possibility of mirroring. That's probably the fairest thing to say at this point. Another way of saying is that, you see, this is something that's magnetic moment is something that's conserved all the time. You can think of magnetic moment also as a current, as a loop. So it's the current times area. Okay, so this is something that's conserved. And so if you take some reference z and take that to be 0, so the magnetic moment at z equals 0 is the same as the magnetic moment at some other z. Either that, or you take current times area. Okay, you use conservation of the magnetic moment and the conservation of total energy, both parallel and perpendicular energy. Okay, so the conservation of parallel energy is this. Okay, the total energy at some reference z, we take it to be z equals 0 here, is this, and that's equal to the total energy at some other z, like that. And you play a little bit of algebra here to get, of course, you also use this, yeah, to get this formula. So the parallel, the quote-unquote parallel energy at a z is equal to the parallel energy at 0 minus like so. Okay, it all depends upon this gradient. Okay, and in particular, when you put z equals 0, this entire term goes away. All right. So as the particle moves into a stronger B field, okay, as this grows stronger and stronger, the parallel component, as this gets stronger and stronger, whatever is getting subtracted from the parallel component becomes larger and larger. Right? So the parallel component of velocity, in fact, could vanish at some point. So at some point, the energy could be all perpendicular. Okay, it could happen that, and this is the point where the mirroring happens. There is no parallel component of velocity at all. Okay, the parallel component of velocity keeps decreasing. So as you're moving this way, the particle keeps slowing down, and energy is conserved, of course. So the slowing down of the particle in the parallel direction is compensated by more furious, wiggling, more furious gyration. Okay, so the particle keeps gyrating more and more, faster and faster and faster as it approaches the mirror point, at which point the energy is all perpendicular and the parallel energy is actually 0. And that is all this level of theory can predict what really, there's really simulations and observations in the lab and in near-Earth situations show you that actually what happens is it's not just that the parallel velocity goes to 0, it can actually the particle can actually bounce back from here, and where it bounces back is called the mirror point. Okay, and this is always possible because there's always nothing is nothing is ever completely quiet. Okay, so even though the parallel velocity technically goes to zero, there can be a tiny little kick, in which case the entire thing reverses. Okay, and the gyration keeps slowing down as you go this way, and at the expense of the parallel velocity, and so the particle accelerates on its way back, and so this would be the mirror. Okay, right. So it could actually get reflected. Where it gets reflected, and if in fact if it does at all get reflected, depends upon the ratio of this ratio. In other words, the pitch angle. Okay, you remember the pitch angle was given by the ratio of the pitch angle was just this. Let me go to the blackboard, and you remember the pitch angle was just how tightly you draw a tangent like this. Okay, and this is the pitch angle. The pitch angle alpha denotes how tight the spiral is. Okay, and and tan alpha is something like that. Okay, or is it the other way around? Is it V parallel or V perpendicular? Please check. Please check this. Either way, no, it's V perpendicular. Tan alpha would be V perpendicular over V parallel. So it's correct, I think. I think this formula is correct.